Alright, so we have been studying dual spaces in this section. So let us start off today by briefly recalling the notion of a dual space itself. Say we are given a vector space V over some field F. Then the space of all vector space homomorphisms from V into F is called the dual space of V, and it's denoted by this symbol V hat, and we of course know that this is itself a vector space over F and its elements are called linear functionals. Now from the result that tells us what the dimension of this space is, when V is finite dimensional, from that result, where in general we do not have F here but W, which is any vector space over F. By that result we have this thing. If V is finite dimensional then the dimension of the dual space over F is equal to the dimension of the original space over F, and hence by that result, which tells us that two finite dimensional vector spaces having the same dimension are isomorphic, we have the conclusion that V and V hat are isomorphic. So V is isomorphic to V hat. As vector spaces, they are one and the same. But the problem here is that one cannot, although they are isomorphic and this comes from theory, one cannot set up a nice natural isomorphism between these two in general. So that thing is not there. But if one takes one more step and considers the dual of the dual, which we can of course consider because this itself is a vector space, so its own dual can be considered, and this is called the second dual of the original space V. Then such an isomorphism exists which is natural between V and this second dual. If you write this thing in detail, it looks like this, which in spite of the fact how complicated it looks, it is in fact something meaningful. Now just like we had this equation, we can of course also have this So just like this isomorphism, we will have an isomorphism between the original space and the second dual. And here one natural isomorphism can be given, and that natural isomorphism is in fact an invariant one. If you recall, we in the previous video itself we said that a construction of anything is an invariant one if it does not depend on any particular choice of basis. So although we need the fact that V is finite dimensional to have this, but we won't use any basis of V or any special property of V to set up that, to construct that isomorphism. So that's what we are going to do today. So let's see how that can be done. So we start like this. Let V naught, we need to write these things now, because this is just simply an introduction. We need to first of all say that V is a vector space. Let V be a vector space over f over some field f. And let v not be any element in V. In the beginning itself, although we will need V to be finite dimensional, but in the beginning itself we are not assuming finite dimensionality, and we will proceed just like this and see how far we can go, and then when that need arises we will assume it. So let V not be any element in V. Now what we are going to do, we are going to define a function t v naught from the dual space of V into f by this relation. F t v naught is defined to be equal to V naught f. Now we need to understand what we have done here. We are defining a function from V hat, the dual space of V, into the underlying field f. That means the inputs of this function are linear functionals in V over f. That means they themselves are functions, that is, they are themselves functions from V into f. This f is one such input. Now what happens when we apply t v naught to it? We get this, which if you look carefully is actually the value of the function f at v naught. Does that make sense? Yes, that makes sense, because you see, when you are choosing f from v hat, then f itself is a function from V to f. In fact, f is a homomorphism or a linear transformation. But after all, it's a function with domain V. So because our V naught is coming from V, we can consider the image of V naught under f, and that image of course is going to be a field element. So one linear functional leads us to one field element. And one more thing of course is that if we have chosen a linear functional f, then for that linear functional, its value at some particular vector v naught is a unique field element. So that is why t v naught is a well defined function. And all these things of course we are not going to actually write here. We will just simply mention that t v naught is well defined. And you can of course understand why we have written t v naught here, because this function depends on v naught. Clearly, this is well defined, but we don't simply want the function to be well defined, we want other things also to happen. So now let f and g be linear functionals and alpha be a field element. What we are now planning to do is we want to show that this t v naught is actually itself a linear transformation. That means it's a homomorphism. We can ask whether it's a homomorphism or not, and that makes sense because v hat itself is a vector space over f, and f of course is also a vector space over f. So first of all, we need to check that t v naught respects addition. So what we do, we have taken any two vectors in v hat, the dual space, so we take their sum, and on that we are going to apply t v naught. So by definition, this is equal to the image of V naught under F plus G. Now you look at this plus, where is this plus happening, or where is it being carried out? It is being carried out in the dual space V hat, and actually by the definition of that plus, which is the vector space addition of this vector space, what is this? This is equal to, because these are after all functions applied on V naught, this is equal to V naught F plus V naught G. And by the way, what is this plus? This plus, note carefully, is actually the field addition. Why? Because these objects are field elements. But why has this plus turned into this plus? That is because that is how addition has been defined in V hat. That's why. Now again, by the definition of our function T V naught, this is what F T V naught plus this one is G T V naught. So if you apply T V naught on F plus G, you are actually getting this. So yes, T V naught does respect addition, but we need one more thing. And what happens when you apply T V naught on alpha F? Because this kind of calculations are extremely abstract, you have to be extra careful at each step. What you are doing, you should have absolutely clear idea about that. So first of all, we are going to apply T V naught. So we will use the definition of T V naught, because that's what we can do at this stage. That means it is the image of V naught under alpha F. But what is alpha F? Alpha is a scalar and F is a linear functional. After all, a homomorphism. Now when you multiply a homomorphism by a scalar, what is the definition of this multiplication? It is just the scalar times the value of the homomorphism at the point where things are being calculated, and that is its meaning. In fact, this is by the definition of scalar multiplication in V hat. And this of course is alpha times. So again you apply the definition. So this becomes F T V naught. So applying T V naught on alpha F gives us alpha times the value of T V naught at F. Hence, T V naught is a homomorphism. But it's a homomorphism from what to what? It's a homomorphism from V hat into F. So that is why i.e. T V naught belongs to this, which is nothing but this. We are putting colon here because this is just a symbol we are defining, and its meaning is this. Note that this is the dual space of the dual space and is called the second dual of the original space V. Okay, fine. So that means, do you see what we have done? We have chosen any vector V0 in the original vector space V, and we have produced an element TV0 in the second dual. So this gives us a correspondence between V and the second dual of V, and we are now going to use this correspondence to show that this correspondence actually is that isomorphism that we are seeking. Okay, now in the next paragraph, let me write from there. Now we are going to define another function, which of course is nothing but this correspondence that I just talked about right now. Psi from V into the second dual of V by this any element V from the original space V. If you apply psi on that, then you get TV. That TV. I mean, from V0 we got TV0 from a general V, because V0 also was an arbitrary vector in the original space V. So just like that, for V we are going to get TV. And this of course is a well-defined function. Psi itself is well-defined. Let us first just simply write that, and then we will see why. The way we have defined TV, clearly for a given V there will be only one such TV. So there is no problem with TV being unique. It is unique. However, does TV belong to this second dual? Yes, that's what we have been showing here, and we have shown here that for V0 in V, TV0 belongs to the second dual. So that is why psi is well defined. But now what we want of psi is that we want psi to actually be an isomorphism, an onto isomorphism. So that will that will then be that natural isomorphism between a vector space and its second dual. But before we go to that, the first thing we have to do is to show that psi is a homomorphism. So that's what we next do. Now so in order to show that psi is a homomorphism, we are going to need these ingredients. We need U, V and W from the original space, and a scalar which, if you want, you can take alpha, but because we have already chosen alpha here, let's just consider beta. The reason for choosing three vectors will become clear now. Note that, so what we are first going to do, we first show that psi respects addition. So we add two vectors, U and V, and apply psi on it. by our definition this will become T u plus v, whereas what is u psi plus v psi, because we want these two things to ultimately be equal. If that happens, then we can say that psi respects addition. U psi is Tu and v psi is Tv. That means we need to show that as functions Tu plus v and Tu plus Tv are the same thing. So that means we have to see what they do to a vector in V, because after all, okay, no, I made a mistake here. We don't really need three vectors in V itself. Two vectors in V are enough, and a general linear functional in V is needed, because these are elements in the second dual. So as functions they will take inputs which are linear functionals, that means which will come from the first dual, the ordinary dual. So that's why we have taken F here. Okay. So now to show that they are equal as functions, we will apply both of them on F, or say we apply this on F and see whether we get this thing applied on F, I mean that they are equal. So what happens when we calculate this? By the own definition of Tu plus V, this is the image of u plus v under the linear functional f. Now this is where the fact that f itself is a linear transformation it will be essential. So f itself respects addition. So u plus vf means uf plus vf. But uf is what? Uf is f Tu, the image of f under Tu, and Vf is the image of f under Tv. But by the definition of addition in by the definition of addition in this vector space, in the second dual, this thing is equal to Ftu plus Tv. But the linear functional f is arbitrary. It is any linear functional in the dual, ordinary dual. So as functions, Tu plus v and Tu plus Tv are identical because they give us identical outputs for a given input. Since this is arbitrary, we have, okay, let me write it at once. Tu plus v, this is equal to Tu plus Tv. This equality is what we are concluding here, and this of course we have already seen, and this is u psi plus v psi, and that is why psi respects addition. Also, okay, now multiplication by a scalar. So what happens when, we have taken beta u, what happens when we apply psi on beta u? by definition this is equal to t beta u, and what is this on the other hand? Beta times psi u psi. This is equal to beta times t u. Now just like before, we see what the effects of these two things are on f. F t beta u is equal to, by the definition of t beta u, this is beta u f. That means the image of beta u under the linear functional f. And again here, because f is a linear functional, so it's a linear transformation, so it itself respects multiplication by scalar. So this is equal to beta times uf, but uf is what? Uf is f t u by the definition of tu. Now if I write this is equal to beta t u, will you understand? You see, tu is what? Tu is an element in the second dual, which after all is a vector space. So it has its own operation of multiplication by scalar. So that means if you multiply tu by this scalar beta, the definition of that operation is actually this, nothing else. So that's why we have this equal to this. But then again, these two functions, this one and this one, they have the same effect on the input f. So like before, they are going to be equal. Again, since f in the ordinary dual is arbitrary, so the two functions are identical. Two functions means t beta u and beta times tu are identical. In other words, beta u psi, which is t beta u, this is equal to beta times tu, that is equal to beta times u psi. So u not only respects addition, it also respects multiplication by scalars. Hence psi is a homomorphism. Okay, now the next job is to show that psi is 1-to-1 and onto. So if we manage to do these two things, then psi will be an isomorphism of V onto its second dual. However, this is where we need finite dimensionality. Assume that V is finite dimensional over the underlying field. Of course, I need ink. This part I have to be careful, because although we are assuming finite dimensionality, actually we don't really need it to show that f is 1 to 1. We will make things clear. Okay, let's just first see where things are going. Assume that v is finite dimensional over f. Now say we want to show that our psi is 1 to 1 injective. That means because we have already shown that psi is a homomorphism, it's enough for us to show that its kernel is the zero subspace of V. So let V be any vector in the kernel of psi. Then the image of V under psi will be the zero element, but zero element where? Zero element in the second space, that is the second dual of V. Then 0 is equal to phi psi. We can, if we want, assume this to be W because we did not take W there, so we can use this opportunity to use another symbol, say W. But by the definition of psi itself, what is this? This is TW. Okay, and this equation itself tells us that the zero that we are writing here is actually the zero element in the second dual of V, because that's where this thing is. So they are equal means this belongs to the second dual of V. But what does this itself mean? This implies, this means that the element TW, because it's a function after all, no, a function whose domain is the ordinary dual space of V. It's the zero function. It's the function that gives us identically the zero element of what? TW is a function from the ordinary dual onto F. So it gives us the zero field element. Where? Everywhere. Everywhere on its domain. That means this implies 0 equal to F0. I am deliberately intentionally writing this 0 a little bigger than this one. This is the field 0, zero element of the field, and this 0 is of course that 0. F TW, but by definition of TW this is equal to WF. Okay. But from this, how can we possibly show that W has to be equal to 0? For that, we have to recall one result that we already proved in the previous video. Namely, that when V is finite dimensional, okay, let me just simply write it without saying it verbally. I probably have not written the number of that result, but in this Herstein's topics in algebra, many results don't have numbers, so we can just simply mention the result. Since V is finite dimensional if W is not equal to 0, if W is a non-zero vector, because you see, we have chosen W to be any vector in the kernel of psi, because psi is a mapping from V into the double dual of, the second dual of V. So the kernel is a subspace of the domain. So that means ultimately W is here in V. Now if it happens that W is a non-zero vector in V, then due to the finite dimensionality of V, there exists an element f belonging to the dual of V. That means there exists a linear functional f such that its value at W is also non-zero. However, here what we see that I did not write that this is true for all. What the hell? After this, there is it continues. Okay, it does not end there. For all f belonging to V hat. That is because TW is identically 0, so it does not matter what your f is coming from V hat on which you are applying TW, you are always getting 0. But if W itself is non-zero, then finite dimensionality of the space demands that there is at least one linear functional which will not vanish at W. So these two things are clashing if W is non-zero. So hence W must be equal to 0. So the arbitrary element in the kernel of psi has turned out to be 0. That is, the kernel of psi is trivial. Trivial means it has only the 0 element. So psi is 1 to 1. Now what I was saying back then about finite dimensionality, and actually we do not need this, that is true, because do you remember that when we proved this result, we mentioned something, that this result in general is true, this one, that if there is a non-zero vector, then you can find at least one linear functional which also does not make that vector 0. This result is really not dependent on the finite dimensionality of the actual space. In the case where the space is infinite dimensional, there also this result is true. However, we did not prove that, citing some reason that the proof will involve some logical things which we are not going to deal with, some set theoretic logical things. So from that point of view, this psi becoming 1 to 1 is also in general true. It does not depend on the finite dimensionality of V. So even if you do not assume this, you can still reach this stage. But after that you cannot go. You will need finite dimensionality. So let's just mention that here also. The fact that psi is 1 to 1 does not depend on the finite dimensionality of V. Why? Because this does not depend on the finite dimensionality of V. but we don't have a proof of that because we did not supply a proof of this one in that case. Okay, because this is just simply a mention of something that we have no logical justification for, so let me put it within brackets. The fact that this is one-to-one does not depend on the finite dimensionality of V. This is because, let us also write the reason. This is because even when V is infinite dimensional, for every vector V in V, there exists a linear functional such that this is not equal to 0. However, we do not have, okay, if I write we do not have, it will sound like in mathematics itself we do not have, do not prove. Okay, let me put it this way, we do not prove this, and as such in the infinite dimensional case, this fact that psi is in general, regardless of the dimension, it is one-to-one, that remains unproved. For us, we have finite dimensionality. And now finally, finite dimensionality forces psi to be onto also. In the text, no further explanation has been given because actually we do not need any further explanation for this. However, I will just say why that is the case. To be onto, but why? Let's look at the function psi. Now from vector space theory that we have seen so far, we already know something, or what I'm going to say now, I may not have mentioned this before, but this is something extremely easy to verify. Consider the image of V under psi, which you already know what it is. It's just the image of V under the function psi, which we denote by phi psi. We already know that this is a subset of this second set, but the fact is that it's not just simply a subset, but this is a subspace Okay. Now our V is finite dimensional, the second dual is finite dimensional, and they have the same dimension. Let's say that dimension is n. So that means this is a subspace of a finite dimensional space with dimension n, say. So from the dimension of a subspace, I mean from that theorem which says that the dimension of a subspace is always less than or equal to the dimension of the original space if it is finite dimensional, from that we get this thing. Okay, but something else is also true. No? We already know, we have shown that this is one-to-one. That means it's injective. So if you replace this second space with the image itself, then your psi, this modified psi is of course onto, simply because you are just considering the image set. But at the same time, psi is one-to-one and it's a homomorphism. So that means psi is an isomorphism of V onto V psi. So they must have the same dimension. But what is the dimension of V? N. So this, although it's less than or equal to n in general, but in this case is actually equal to n. Now from the dimensions of vector space, from the general theory of dimensions, we know that in a vector space of dimension n, we cannot have a proper subspace whose dimension is also n. If you have the same dimension, they must be exactly equal, and that's why this must be equal to this. From this follows the ontoness. So that's why finite dimensionality forces psi to be onto. And this thing, although it looks somewhat complicated, we have actually done this before. In the special case where we had a homomorphism or a linear transformation from a space V into itself, which is one-to-one, and the additional condition that is imposed is on V, that it is finite dimensional. If this is the case, then we were asked to prove that this T also then has to be onto, and this is just that, but we don't have the same space. That's the only difference. But this is onto. So now you can see that we have achieved an isomorphism psi from our original space V onto the second dual V double hat. And in this whole thing, in this construction of the isomorphism, we have just simply used the fact that V is finite dimensional, but we did not use any basis of V. We did not, for example, choose a basis and then using that basis we constructed psi. No, that's not the case, and that is why this construction is invariant. So let's mention that now. But before we mention that, let's just state this thing, what we have achieved so far, as a, what is it, a lemma or theorem? What is lemma? And the lemma is just simply this: if V is finite dimensional, then the function psi defined above is an isomorphism of V onto the second dual of V. And now we write, note that since the construction of psi does not depend on any basis of V, it's an invariant construction. It's an invariant one. And because of this isomorphism, we will henceforth identify the original space with its second dual. That is, we will treat them as the same thing. Because of this, we will henceforth identify V and V double hat, but keeping in mind that this identification is being carried out by the isomorphism psi. That means you have the space V here, you are going to treat it as the same space as V double hat, and the mechanism that will allow you to do so is your psi, which allows you to treat an ordinary vector V in V as this thing dV in V double hat. Okay, so that's how we are going to identify, and in fact this identification will help us in the things that come next, which we will see in another video. The next thing, the first thing that we will see next is called the annihilator of a subspace of W. If in your vector space V you have a subspace W, you can consider all those linear functionals in V hat, all those linear functionals which vanish completely in W. That is, no matter what vector you are choosing from your subspace W and put that vector in the linear functional F, it's always 0. So that collection of linear functionals becomes a subspace of the dual space which has some properties. Okay, and then from that we will see that many other things follow. So we will see all these things but in the next vector space update. And tomorrow, because we have already gone through Galilean's group and ring exercises once again, so tomorrow we are going to go back to Lee's algebra exercises. So that being said, this is just it for tonight. See you tomorrow with Lee algebra exercises. Until then, this is me, Lucifer from a mathematical room. Have a nice night.